Thank you all for being here. It's my first time at CppNow, so my first CppNow talk. So what I was thinking is hour and a half talk. I have about 70 minutes of content, so we can reserve time at the end for questions, or you can just jump in any time. It's a small room. I'm really happy to kind of dig into things as you wish. Okay, so it seems like memory safety is unavoidable now, right? We have many examples all around. I think one of the most notable ones was last year there was a White House memo encouraging the industry to kind of move towards memory safe languages. At Google, where I work, we had a report last year which came out, kind of also focusing on this idea of a kind of memory safe future. I saw some of the early drafts of that, and I remember it was rather surprising to see not only that someone actually gone ahead and written it, but the amount of kind of excitement and support for that position. So I've been in the industry since the early aughts. I've been at Google since 2012, and kind of being concerned about memory safety was always a small group who cared, and everyone else, had it was never the most important thing. So I think it's interesting to ask, what changed? Why now? Even just a couple of years ago, this was not nearly as big a deal. And I think there are two key answers, possibly related, but I see them as essentially independent. The first one is the success of Rust. And so it's not just the appearance of Rust. Rust is, I think, more than 10 years old at this point. Soon by 2016 it was on the scene. But its actual kind of increasing adoption within the industry has said that within this niche, within the area of high performance computing, there's a real alternative, which is memory safe. And so competition, does its charm. And now folks, on our side in C++ really have to kind of be concerned, well, how are we going to compete with Rust? How are we going to be memory safe or something close to that. But that's not it. I think there's also this shift within the security community itself, this kind of increasing realization that just detecting the next problem or mitigating against the next problem. So all the sanitizers, UBSAN, ASAN, MSAN, which have been kind of real success stories while I've been at Google, and definitely valuable. They're all about kind of detecting, and that helps you in debugging and whatnot, but they're never going to stop kind of the next exploit. You're always playing a game of catch up. And the same with the mitigation. So ASLR and Pi. And I had this firsthand in 2014. I was on an ads team, which was doing some greenfield development. We had to decide which language to use. And we considered some memory safe languages, but one of the answers we got was, well, there are all these other protections when you're running the code that the language you choose really doesn't matter. And so all of that has kind of gone out the window. There's been just this major shift to say that no, that we can't constantly kind of play this game of catch up, of trying to kind of get the next bug, that we have to kind of move forward towards memory safety. Okay, so I'm on the actually the lead of the C++ static safety team. So there are a few safety teams, right? And there's a bunch of different C++ teams. We're all working together towards this kind of view, this future of memory, of safety for C++. And the key idea here is that we want to kind of incrementally drag C++ towards some form of safety. And it's not like we think we're going to get to a safe C++. Okay? We have no illusions, but saying that we can never get to perfection doesn't mean we can't make things better. And that's our goal. It's kind of piece by piece make things better. And the compromise we've struck is to say we're going to identify bug classes and rule those out. And that's why it's static safety. It's about the language. It's about kind of the compiler, what you do with the developer before you even get to, say, running a test. Kind of at that point, rule out a bug class, and then you never have to worry about that again. There'll be others for sure. You kind of piece by piece kind of make the language safer. And another way to put this is kind of, we feel the only way to win is not to play the game. You can't constantly be kind of fighting the last the next battle. Okay, but stepping back from memory safety, what is safety in general? And this is something that kind of comes to me from my experience in academia, programming languages back when I started. Robin Milner's quote from '78, basically saying that a well-typed program can't go wrong. Okay, and go wrong in that context is a theoretical notion. You actually have a formal definition of your language, and you have essentially error states. And the idea is if it's well-typed, it can never reach an error state. But that's really just another formulation of the notion of a safety kind of principle in general. And I think translating into our space, I would roughly say that that's saying that if it passes the compiler, then there's no undefined behavior. And kind of going back to Shahar's talk, I think this is an important, this is not exact mapping, but I think that intuition is there. The idea is that you feel like once the compiler says it's okay, you should actually be guaranteed that none of that weirdness is going to happen. Now, it doesn't mean it won't go wrong in the sense that you won't have bugs in your program, right? So what does it mean? means that there are fundamental invariants of the language, kind of just fundamental assumptions without which essentially nothing is meaningful. Like, you just have one big array and you can index into that. That's your memory. So we don't like that. We want to actually just say that if something has a type, that type has meaning. And so the basic idea is safety means that those invariants will be preserved and you can rely on them, whether it's the optimizer or you just as the developer can rely on them. Okay, so we tend to break down the notion of safety into kind of a whole bunch of subsections. That first group you might recognize as one way of presenting memory safety. So it's got spatial safety and temporal safety. I'll go into a few of what these mean. Type safety, initialization safety, data race safety. Those are grouped together. That's memory safety. But there are more besides. And again, going back to undefined behavior, pretty much any example of undefined behavior kind of maps onto some notion of safety, which is you will not hit that undefined behavior. So if we want to talk about not hitting a null pointer dereference, well, that's going to be null pointer safety, integer overflow safety, let's say. Okay, so for this talk, I'm going to focus on 4 of these safeties that my team has been working on, specifically spatial safety. And so I'll define that briefly as you have essentially a contiguous piece of memory, and you mean to index into it, and instead you index out of it, so an out-of-bounds access. Now, you're accessing invalid memory. So it's no different in some sense than any other invalid memory access. So this is really something, it's just a conceptual idea we've come up with to define it that way, to say you meant this, you did that. But that is still a useful kind of class of bugs in which you're trying to access uncontiguous and miss. Temporal safety also talks about invalid memory, but it talks about it in time, where say at one point the memory was valid and now it's no longer valid. So that's use after free, or a kind of a specialization of that where use after return, where it means you've taken an address from the stack, you return, now it's no longer valid, and then you try to use it. Or double free, which is just, again, a special instance of use after free, where your use is trying to free. And then we have initialization safety. And this is the idea that like uninitialized memory can cause problems beyond just kind of giving you garbage. So initialization safety means you have no use of uninitialized memory. And then finally, null pointer safety, which is you will not dereference a null pointer. Okay, and before I go on and tell you about what we've been working on, I just want to kind of set the stage here that our solutions are constrained by the scale of Google's operations. So that is a major kind of factor in any solution we come up with, is trying to deal with the fact that we have hundreds of millions of lines of C++ code, of which there are tens of millions of pointers. Let's say pointer declarations, meaning either an actual pointer is declared or there's some type in a declaration which contains a pointer, like a vector of pointers. We have millions of files. And this is relevant because you want to automate edits. You want to touch many of those files, or all of them. You have to just deal with the raw fact that you're making that many edits. And finally, stepping aside from the technical details, the personal details also matter. We have tens of thousands of developers, which means even a small change, if it's not well planned or it's the wrong change, you're wasting the time of tens of thousands of developers. And conversely, we are a small team, which means even just a small percent of tens of thousands of developers are unhappy with your change, you will have to answer all of those developers, whether it's comments or bug reports or the like. So you have to really be careful to make sure that the way you go about doing this kind of takes the people into account. Okay, with that, let's get into null pointer safety. The basic problem from our perspective is that C++ conflates these kind of two rather different ideas. One is you have a pointer to something which always exists, and one is you point to something which is optional. It doesn't have to exist. Worse than conflating it like by default, it does not give you a means to distinguish. Now you might object. You might say, well, we have references. References, by the standard, it's undefined behavior if they're null. And that's true, but references are actually subtly different than pointers. It is not the same thing to say that a pointer can never be null and a reference. There is an overlap. There's a substantial overlap. By our accounts, probably about 50% of non-null pointers could in fact be references, like construct, for example, but they're not the same thing. So we still care about this notion that you should in language be able to distinguish between optional pointers and required ones. And this has a number of bad results. The number one for us, probably what motivates this project when it started, is just outages, right? We all know, like, if it's your program, a null pointer crash is annoying. When you put that at scale, we're talking about huge number of actual production outages caused just because null pointer dereference. So if you're interacting with a service and suddenly doesn't respond, well, it could be because the task crashed because of a null pointer dereference. That's not good for anyone. And it turns out a large percentage of the crashes that we see in C++ binaries are in fact caused by the null pointer dereferences. Okay, it's also a tax on the developer. What surprised me kind of after the fact, once we started kind of working on this at scale and modifying much of the code in Google, is that when you look at an API and it's annotated, it's suddenly just easier to read in a way that I had not anticipated. When you look at an API and you have pointers in it, whether it's an argument or whether it's a return type, you're constantly subconsciously trying to figure out, or maybe not subconsciously, figuring out, can that be null? Is it allowed to be null? Once you kind of distinguish between them, that goes away. And finally, we're looking towards this memory-safe future. A key step towards that is the notion of interoperation between C++ code and Swift or Rust or Carbon, Safe Carbon. And to do so, you're talking to languages which already distinguish between nullable and non-null pointers. If you can't do that in C++, there's this impedance mismatch. And either you kind of map everything onto a nullable pointer and shrug and it's just clunky, or you kind of have to just hope for the best. Okay, so the obvious solution I think kind of might be coming out is, well, we want to go ahead and change the language. It doesn't let us distinguish, now let us distinguish. Now, changing language is a lot of work. I think there are people here who work on the standards committee or work with them. So we're starting with just a conservative extension of the language. And the basic idea is let's add annotations to pointers, which let us kind of specify the meaning, this distinction, and think of them as kind of API contracts. They're contracts, well-defined meaning. They're not an actual change to the language, but they do give kind of helpful information to the developer. Okay, so we're adding annotations. So let me just take a pause here and say, fine, you have the language as is. You want to add some sort of annotation. And anyone kind of want to guess? If you're doing this, what do you want to add? Yeah, please.
Nullable.
Okay. Yeah, that's a possibility. Any others?
Non-nullable.
Non-null. Okay. Anyone here interested in both?
Clang has these as extensions, right?
Yes, it does. We'll see that. Yes.
Unknown, maybe?
Yes. So legacy, and that fills out the collection from Clang. Okay. So the argument for non-null. This was, I think, Matt. You can say, well, the semantics are nullable, right? If you have a raw pointer, it's nullable inherently. So just add non-null and done. You just need one, and then that's all you need to learn. So someone's going to counter and say, no, that's not true, because the semantics is true, but the semantics of the language, anything is nullable. But the whole point is in a given program, something might be nullable and might not. So that's not what I want. I want to be able to call out when something is nullable. And that way, I also don't have to worry about false positives, because otherwise I have to assume everything's nullable, right? So now I've resolved that. But now I have no way to express that something actually can never be null, which you can do, say, with a reference. I want to do that for a pointer. So now we say we want both. But then what do you do with the raw pointers? So basically the idea is that there are actually three states. And this is a really crucial kind of insight, not our own. Non-null is the invalid, is the state that null is invalid. Nullable says that null is valid. And those are distinct states, and they're distinct from a raw pointer. Raw pointers are legacy. We call them unknown, but you can call them unspecified. But the key point is that we don't know, right? The language conflates them. The whole idea of conflation is there's two possibilities. And nullable is a very distinct possibility from just I don't know. So we call that out as its own state, possible state for pointers. And these map into three corresponding annotations. For Clang, and I'll be using these for the talk, they've existed for a few years thanks to Apple's work with the, I think, Objective-C. It was a Swift or Objective-C, maybe both, interop. And we also export them in AppSale, in case you're not using Clang, using that alternative but very closely related syntax. On the right side of the slide, I have some very simple examples of this syntax. You might mark, foo's argument is non-null, and you can see it's just right there to the right of the pointer, or bar returns a nullable pointer. And then zab here, which is unmarked, that's implicitly, unknown. Now we do have an explicit specifier for unknown. It's very long in both cases, and that's not, I think, an accident. You don't really want people writing that, but there are times that you do want to say that explicitly, so it exists. But mostly that's kind of implicit. It means that no one has gotten around to updating it. Yeah.
Did you intentionally use underscore capital?
No, that's from Clang. I don't know the history of that.
It's undefined behavior to define such a...
So it comes from the compiler defines it, that's okay.
Yeah, but Right.
Yeah,
That's why I asked if they intentionally used this method.
yeah, that's
Probably
like
yes.
the C standard likes doing, stuff with the underscore uppercase, and that's probably where
Right.
they came from.
Mangled functions that translate to underscore uppercase and stuff like that. So if the compiler does that, it's probably okay. But the user-defined symbol is not allowed to do that.
Yes, so for ABSO, we didn't do that. There was a long discussion as to whether we would have uppercase or lowercase, but that is clearly different than the question of the leading underscore.
What is Spatial?
So Spatial is Google's, basically a large collection of Google's standard libraries were open sourced. I don't know,
2016.
Yeah, 2016. Right, yeah, you would know well. Andy worked on that. And that's kind of the means by which we open source kind of most of our software. We definitely, there's other efforts, and you can kind of throw things over the wall as well. This, for example, is not in ABSO, the checker. I'll get to that. But that's, if you want to do it right and with kind of guarantees about support and all that, that is our kind of open source library. Okay, so contracts are nice. They're nice just for communication, but we also add enforcement. That's been a major part of this project, is kind of a high precision enforcement mechanism. These are really simple examples, but they should stand to illustrate. So the first one there, F on the top left of the screen, is a non-null parameter P. And the key thing there is we don't warn about it. And that's kind of, part of the point, that you can dereference P since it's guaranteed, it's marked as non-null. That's the contract. You don't have to check it. So there's no warning. So there's that lack of false positives we talked about. Then if you mark it nullable in the second example, and you do the same code, now it's going to warn. So very simple example. Now that code could be, 1 line. It could be 100 lines. If it's nullable and has not been checked, then you'll get a warning. On the right, we see a kind of a very simple fix to that, where you check it, you make sure it's not null, and then you use it. And in the other branch, you don't use it at all. And so there, that's fine, no warning. That's the basic model.
Is it?
Yeah.
You go back.
Yeah.
In the non-null case, if somebody happened to check for null pointer, would you also warn, or is that just like?
No, that's a good question. I would like to someday. I'll put it that way. I think that's a performance thing. This is a redundant check, and you shouldn't have to. At this point, though, the contracts are not enforced. They're enforced locally within the function, but between functions, if someone calls you with I'll get to this, with a legacy pointer, they're kind of treated optimistically, so you can't really rely on that. So it's up to the user how much they trust their callers.
So do things like, for example, an assert suppress that warning as well?
Which one? The one on the bottom left? Yes, absolutely. Assert would be a very good way to suppress
Even
it,
if like debug or non-debug, the analyzer still looks into assert. Yeah.
Yes, because the analyzer runs essentially in debug mode, so it will see the asserts.
Okay.
Yes, and so that is a way. So in subtle code, which we cannot reason about, one of the recommended ways is just assert it, and then the analyzer knows it's true, and goes on from there. Okay, I said this is a conservative extension. This is kind of a crucial feature. And that means, again, it's like a contract. You're specifying the expectations, but it's not any sort of guarantee. If something's marked non-null, null could flow into that. In fact, a reference null can flow in, but at least that's undefined behavior. In this case, it is not undefined behavior. It does not affect compilation. You can't really meta-program on this, and that's by intent. Again, as part of the challenge of working at scale, you want to be able to go ahead and change the code throughout the company. And if suddenly there could be some subtle dependency on behavior based on whether something is null or non-null, that means we could have unexpected results in production. Now, you can do that. You can choose to make changes to the code across the code base, which will have an effect. That just demands a very different deployment strategy. And so for this project, we want to keep it simple. So it should not, it's like guaranteed will not have any effect, and we don't have to worry that we're going to break someone's code. It could break in terms of compile time. There are some cases there, but you're not going to actually change any behavior. And finally, this is a subtle thing which came up actually because a user pushed back on something, asking if it could cause UB like with a reference. And the answer is no. These are just contracts. No, the compiler will not take these into account. There is no UB. Okay, there's UB if you dereference a null pointer, but not from violating a contract on a pointer. Okay, in some sense, this is what I'd call a gradual analysis, or ideally this would be a gradual analysis. And this gets into this idea of what does unknown actually mean? And so on the example on the left, we have a function which takes kind of a legacy pointer, called unknown, And then the nullable pointer P is passed to that. So we assume the best, which is to say we don't know what that is. So we're going to assume we can pass something that is knowingly nullable. We can pass it to G. But on the right-hand side, we have the flip. G now takes explicitly non-null. It says only pass me non-null. Now we have some legacy code F. It passes the pointer P. P, we don't know what it is. So again, we're going to be optimistic. We're going to say we're going to assume that it meets that contract. And by this means, we reduce the false positive rate. Now, in kind of the proper gradual analysis, this is kind of inspired by the paper quoted cited below, you would then insert a dynamic check anytime you had one of those kind of boundary crossings. And then you're guaranteed from the outset, you basically can just turn on a flag. Your program now is null safe in the sense it will deterministically trap if null is used in a way it shouldn't be.
So just a question for the right example. So from that point on, after the call, P is assumed to be no. It means like all the relevant warnings will be emitted in cases like, for example, if you use a P, or for example, exert P is no or something, then it's going to generate a warning or something?
I don't think we do that. That's not a bad idea.
Yeah.
But there isn't any warning. I mean, since it's unknown, there isn't any reason to assume, like they wouldn't help us because we already don't warn. And in fact, the implementation is we basically have a separate Boolean which tracks whether we know what it is or not. And if it's unknown, we just don't warn on it anyhow. So that would be an interesting idea. It could give us some benefit, but we don't do that right now. Yes, but it's more as in the local context, it will definitely kind of make sure that it does not. Okay, and the idea is we don't insert a dynamic check. We're not integrated into the compiler. We're integrated into clang tidy. I'll get to that in a moment. But that would be kind of ideal. However, that would violate this notion of being a conservative extension. And so there are some interesting ideas there. I didn't have time here, but we can talk about that if there's interest. Okay, so another key feature of this analysis is that it's intra-procedural, or kind of just it's function by function. And this kind of cuts both ways. In the positive, it means that the whole function scope is in play. So it doesn't mean you just have to locally know. So kind of rewriting the example from earlier, you'll notice if you have a function and you check whether something is null pointer, P is null pointer, if it is, you return. 100 lines later in that function, that's still valid. As long as you haven't assigned it to P, overridden it in some way, null works. We're not requiring that in the local scope of, say, an if condition that that only there can you kind of rely on that. On the other hand, it also limits you to the function scope. So in the example on the right, even if you have a simple helper function is null, and then you use that to check the state of the variable, our analysis will not pick up on that. Now, for the most part, we actually think of this as a positive. It leads to what we consider gradual modular reasoning, so that the developers generally don't reason well between functions. For a helper function, it's all well and good. What if it's a little more complicated and someone goes ahead and changes the meaning of a helper function? Suddenly, your code isn't working anymore, and trying to figure out why it isn't working, and then you need an explanation, 3 levels deep in the call stack as to why your assumptions no longer hold. For most people, that's actually not a good experience. And so this is the kind of thing where maybe helper functions, we could analyze. In fact, we do if it's a getter for object fields. We will read that and interpret it. But for the most part, we think this is a better approach to reasoning about generally about safety.
But isn't the whole point of automatic verification that to fill in the gaps where human verification isn't good enough? Can
Yes.
you trust your future self to run the verification and catch the problem?
So, yes, but I would say you'd be surprised by how many, just local reasoning. I'll give you a quick example. We got a bug report saying, it's telling me I haven't initialized this variable, or I haven't, initialized a non-null before dereferencing it, but it's initialized in both branches. And we look at the code example, and there are actually 3 branches, not 2, because it's like a nested if. So this is the thing where they saw a problem, they copied the code, pointed us to it, and they in fact had not noticed that in their own code. They actually had 3 possibilities, 2 of which had initialized them to non-null and 1 had not. So I think there's a lot that goes on even in the local scope. And the idea is that you should be able to reason only within the scope of the function, and then have annotations on at the function boundaries which capture what you need to capture.
There's also the important issue of Pyro saw, maybe the function now returns a pointer that is always not null, and you could detect that, but that wasn't part of the contract that the user who wrote the code. In their next PR, it's going to change, and you don't want everybody else's code to warn because of that.
Yeah, exactly.
This is a little unfair, but why isn't there a notation that you can put on is null that says if the function is returning true, then the thing is definitely null, and if the thing is returning false, it's definitely not null?
Yes. So there are many. Yeah, we could go down this road. And there are, I think, a lot of ideas. We have a bug filed asking exactly that question. Should we consider a logic, basically? And I don't get into it into this talk, but the implementation of this analysis actually has an entire logic backing it, and it lifts expressions into logic. So doing that wouldn't be too hard. The real question we have is it a good idea? Like, do you want users doing that? So another option is to annotate a helper function like, helper, right? And then that means is to go and interpret that. We actually do have support for going and interpreting, helper functions. But that's another question. Is that a good idea? Does that scale? So this is really, to me, the exciting part. This is language design. The limitations here are not technical. They're really about actually people. There's more we do that we tailor to kind of users, which was, anyhow, there are a lot of interesting questions that have to do with how will users understand this and how will they interact with it, and they weren't about our technical limitations.
It's also worth pointing out it is way cheaper to not have it initially and give it to people later than it is to take it away from them if you realize you made a mistake.
Yes, I have more stories on that too. Months worth of lost time stories. Yeah, talk to me afterwards about AutoStar. Crying on his shoulder. Okay, so this is a good start. Basically you have something that's function scope. We kind of, gradual, so it reduces false positives. Actually, sorry, Matthias, did you have a question?
No.
Okay. And this gives us a strong foundation for essentially what we call incremental deployment. The idea is that you can go in, you can kind of change one piece of code, you don't have to worry about changing the others, and move on. You can keep on incrementally updating your code base. So it's nice. This is like a mechanism, but it doesn't get us from essentially 0 today, which is, I think, we have less than 1% of the code base annotated, to where we need to be, which is, say more than 90%. After more than 90%, I don't think we have to get to 100, but 9% plus, I think you can pretty much rely on the annotations. We'll see crashes in production coming down. It'll just be a fundamentally different experience. So how do we get there? And the idea here is inference. We're going to do automated inference by looking at the code base. So your challenge is your inputs are the code base, and your outputs are for every single pointer declaration. Tell me whether it should be non-null or nullable. Ideally, nothing is left unknown, but maybe some small percent of that would be acceptable. So I gave this away. I meant to kind of have asked you for ideas, but before I explain this, let me just throw this out. So if you're going to do automated inference, all you get is the code. Any ideas like how you would try and guess annotations based on just looking at the code?
Do they test it for null?
Nullable is
Okay. So a test, if p equals null. Okay.
Annotating with nullable is easier or has less false positives than annotating for non-nullable. If you see something that can be null, then it can be null. But if you don't see it ever being null, it doesn't mean that it's non-nullable.
True. Okay. Any other ideas?
I mean, the simple one is if you dereference it, then it has to be null.
True, but if you dereference it at all, only dereference it in a certain context. Do you want to kind of refine that?
Did you mean to put the answers to this question on the screen while we're answering?
No, I didn't. So as I said, I mentioned not, but I figured that before I explain it, I can coax it out of you. Yeah. So dereference is more subtle than you think. You actually have to check that in that context, you don't know already that it's not null. Right. So parameter binding means the call. So I don't know if anyone mentioned that if you have a bunch of callers, if even one of them passes null, then you can guess that you can say that has to be nullable, or you'll have a problem. Assignment works for nullable, but not for non-null. So if you assign non-null to a pointer, you don't really know if it's going to be non-null, because it could also get null. That kind of gets to your point. But if it's assigned even once from nullable, then yes, it's going to be nullable. So to your point, Matt, about Boolean tests, this is an interesting one. We actually don't use this. And this comes down to kind of a reluctance to rely on what we consider defensive coding. So you see this a lot where actually, if you actually look at the control flow and how the program works, there is no way to actually pass null to that parameter, where people see a pointer, and they just kind of reflexively check that it's not null. And then often like there isn't really a good thing to do with that. So we have a design for taking that into account, and we think we probably will eventually want to use that. We're hesitant to kind of use that up front before we've used everything else that we can.
What about asserts?
So asserts are different. Those we do take into account, but it's a different, the means by which we take asserts into account are different. Yeah, Z.
If you pass it to a function that expects non-null or nullable, can you use that as information to propagate up? Or?
So there's the opposite. If you pass to a function which expects nullable, fine, it doesn't tell you what it is. But if you pass to a function which expects non-null, yes, then that has to go up. And that's like the same as dereference. You can think of dereference as an operator which expects non-null. So that will propagate backwards.
So does your analysis also run inside of another one that's taking reachability into account? Because maybe you're gonna see some code, they're gonna try to infer something from it, but they don't even know if that code is reachable or not. So is this concurrently running other kinds of analysis that are trying to see what parts of the code actually matter here?
Sort of. So we don't do reachability, but liveness is taken into account by nature of the basically the logic we use to model what's going on. So if you have a branch which is fundamentally dead, which it says, if p equals null pointer, but we already can tell that it's been checked and it can't be null, then the logic basically, nothing is true within that block, and therefore nothing holds, and you can't accidentally learn something from it. So it kind of falls out from the design of the logic that it does take liveness into account, or dead code into account. Okay, so just a quick example here, or two quick examples. On the left-hand side, you have get, which will return null in one of the branches. It's not in both of the branches, but then it will mark it nullable there on the right. And that simple example from earlier, where it dereferences it, it hasn't checked it. So now, in order for that to be safe code, it must be the case that it's required that P be non-null. Okay, so this gives us kind of a basic foundation for nullability.
Aren't you just setting in stone the current bugs this way?
It's more like sitting in clay.
Yes. No, that's a good example. So to some extent, yes, but there is something working in our favor that as long as they're actually bugs, right? So if you dereference, say, a pointer P without checking it, and someone passes null, as long as at least one of your clients passes null, you'll now have what's called a contradiction. We'll detect the contradictions. The contradictions we don't do anything. Or what we're doing now is going to actually annotate them explicitly as there's a contradiction in your code. You have to take a look at this and resolve it. And we plan in the future to actually add tooling to kind of. I think there are cases in which we could figure out better. Some we can be relatively positive one way or another. So that's kind of, I'd say it's open future work, but at the very least we're setting that aside so we don't set in stone mistakes. And there actually is a previous iteration of this project which we were not involved in, which did exactly that. And we actually have a client team who's been asking us to remove all the old annotations that were automatically inferred and replace them using the new system and calling out those differences, where there's a contradiction. But yeah, there are other things we can still set in stone. So fundamentally, you are discovering what's true today of the code. And that is a compromise we have to take if we are going to automatically update tens of millions of pointers. Okay, so this gives us a basic foundation for nullability at scale. This kind of conservative language extension lets us kind of move around quickly in the code base without worrying about breaking things. That gradual modular analysis, so it gives you incrementality, automated annotation, and in addition, the analysis, which I didn't get into too much, is very high precision, which means developers don't get angry at you. Well, they don't get too angry at you, in the sense that we can handle a large variety of existing patterns in C++. Don't force them a priori to kind of conform to what we'd like to be, or to simpler patterns, and therefore fewer kind of false positives. Okay, so let me just kind of jump into a few more details before moving on to kind of the next topic. One is, this is all very nice and good, but someone here in the audience must have been horrified at thinking of all those annotations on tens of millions of pointers. And so we don't want to do that, right? We don't want to say every pointer is annotated. Let's leverage the default, kind of the raw pointers that we all know and love in C++ for something. And we can do this because there's actually an imbalance in the ratio of the two types, non-null and nullable. So I've covered this up This time I did it right. Anyone want to guess what the ratio is? You can either on Google code, third-party code means just kind of general code that we use. So that's a random sample of code from across the community. Yes.
So this region annotation, how does it take template instantiations into account? So is that from the region where the template was defined or where the template was instantiated?
You mean the inference?
Yeah, that region annotation, you mean?
Oh, that.
Yes.
Yeah, let's not get it. Yeah, so we have different semantics. Cling and we have different semantics. Yeah, I can get into that afterwards.
Okay.
It's interesting, but I think I'm just it's very much a detail. But in terms of the ratio, anyone who can guess at what you think the ratio in code of?
I bet Google code is 8-to-1 and third-party code is 2-to-1.
Okay. Any other guesses?
I was going to guess 4-to-1 and 1-to-1. The same.
100-to-1 and 1-to-1.
I cheated. You always one digit.
Yeah, 6-to-1 and 4-to-1. So non-null is actually overwhelmingly kind of preferred. So this says that we can actually assign non-null as the default pointer, the default meaning. Once we get there, we would like to reuse it as the default meaning, and then we only have to put, 1 in 4 or 1 in 5 or 1 in 7 annotations as nullable. But again, the default meaning now is not non-null. So we have to get there. The way you get there is with this kind of region-based annotation. So Clang actually has regions begin end. We have a whole file. They're both region. The idea is you're saying within this region, or within this scope, all the default meaning of our pointer is non-null. And then if you want it to be unknown, it exists. We have that annotation. You just put that instead. Yes?
So let's say you get there. I mean, you annotate the whole code base. People are writing new code. And then if they forget about the default being non-null, how do we deal with that?
So are we talking they forget in the sense that they create a new file and don't mark it as such, or they forget and they're in a file that's marked default non-null and they forget?
How about both cases?
How do you mark a file?
The second piece is
Wait, no, you said mark a file. How do you mark a file?
Yes. So the way you mark a file is there's a declaration at the top of the file, or anywhere in the file you put there, and from there on, the enforcement mechanism, the checker, will interpret all raw pointers as non-null. So what happens there, the nice thing about that is that once you've done that, any pointer you add to that file, it has a meaning. And if you don't obey that contract, it will warn. It will say, this is non-null and you're not using that way. At which point you're like, oh, I didn't mean to use that way. So you just mark it nullable.
What if your header and CC file disagree?
That's fine. It's per file. So they can't disagree in the sense of it will give a different meaning. It doesn't give a different meaning. The point is they can use different conventions. That's a bad idea, but they can't disagree. So there is a check specifically to make sure that the actual semantics, that contract you put on the declaration matches the declaration inside the CC file.
And if you forward declare someone else's stuff?
If you forward declare and use it, I don't think, if you're forward declaring, you're not going to see their declaration or their implementation. So that's on you. Yeah, I don't care at that point. There are only so many things I can worry about.
Private public, right?
Stuff happens.
Okay, so where are we on the analysis? As I mentioned, this is implemented as a clean tidy check, so that's not integrated into the compiler. It's been released in the crewbit. It's one of our smaller OSS repositories. This is the kind of, we can throw this over the wall style. But the good news is it's built on Clang's Dataflow framework, which is an upstream framework, and we do plan to upstream it to make this more widely accessible by the community. We enabled this check for all of our first-party code more than a year ago. We've only got a small number of kind of false positive and false negative patterns. On average, we see about 1% of the diagnostics that users see they go ahead and mark as not useful. An interesting tidbit here is that a lot of the reports we get are actually mistakes. And I don't mean this to make fun of users at all. I think it's kind of a lesson to us that sophisticated analysis are sometimes too sophisticated for their own good, or you have to be careful to really work on the kind of education and diagnostics. So we are investing on kind of clearer diagnostics, explaining better and whatnot. But we also need to invest in terms of documentation and just generally kind of some of the classes we do within Google to help people understand what they're looking at when they deal with this new system. And for inference, we're about ready to start our first phase of annotating the code base at scale. We see about 75% of the pointers we can infer with what we call high confidence. That means that kind of a validation. The system thinks it knows what it's talking about. 100%, we actually look at it, it's nearly that. So it's actually acting very accurately. 3% of these conflicts we mentioned, we see evidence in both directions. 3% there actually is no evidence. Like if you look at the code yourself, you're just like, I have no idea what the developer intended. And in some ways, it's a pass-through data structure, which maybe just doesn't care. So it's a polymorphic in the nullability. We're at, actually probably a little lower at this point, but when we sampled this data, about 19% what we call model limitations, like assorted reasons why we know the answer, but the model couldn't get it. About 2 to 3% of those were situations like a nested pointer, like a vector of pointers or optional of pointers, which we think we have a good way to address. That's just kind of work that needs to be done. Yeah.
So you talked about functions that are polymorphic and nullability, and that's really interesting. Is there a way to mark a pointer's polymorphic? Because polymorphic is different from raw or unknown, right?
Yes, the way you mark it is with unknown right now because it's just like, you can encode it with like a Boolean, a template with a Boolean parameter. But no, we do not have an actual polymorphism. We don't have an annotation for that, which would be awesome. But again, future work for language design. It doesn't come up that often, though, surprisingly. But yes, it would be nice to support. But that's the kind of thing I think we'd like to. We like to basically have there's 2 annotations you have to learn as that normal user, and then advanced users can do a lot more. Okay, the one key point I'll throw in here is that with kind of guesses, if you actually look at the data and kind of say how often is it non-null versus not, and is it parameter return, you can do a breakdown, and LLM could probably do it even better than we've done it by hand. But basically, you can have a statistical model and kind of come up with really good guesses. If you then guess for that, 19% or again 15%, which we have left, you'll end up with a system which is more than 95% correct. We think, again, we can get to say 97% correct. And then there's the question, is that good enough? And that's what we're trying to figure out now. Phase 1 is going to focus on just rolling out high confidence annotations, where our next work is try to figure out, working with early adopter teams, are they okay with this 97%? Or can we do better? Or do we have to do that?
Once you've rolled out the 75% of high confidence, is the assumption that the ones with no evidence will suddenly sprout evidence?
No, the no evidence, which I call no evidence, those really, you just look at the code, there isn't any information in the code for those. But yes, I think there's others in the say the 90%, that there was definitely ones we see there's knock-on effect. The fact that there was, say, a conflict and therefore there was no marker there, that's why they didn't get an annotation. So yes, I think once we kind of fix those and once we fix the conflicts, we do expect there will be positive impact from that as well.
Sorry if I missed this, but what's the ultimate output? Does a team get build output that says, hey, you have some contradictions, please fix them? Or does a team get patches that say, please apply these nullability annotations? How does that work?
No, that's a great question. You didn't miss it. I didn't say it. Right. So Clean Tidy is integrated into our review process. So when you're doing code review, anytime you do a checkpoint on your patch, it will trigger a whole bunch of analyses, one of which is Clean Tidy. So you'll get these reports and they'll kind of come back on your code review. The reviewer will see it, you'll get to see it, and you can kind of decide whether to act on it or not. That's one method. We also do a daily run over the entire code base, and we export that in a database which anyone can query. That's also integrated into our internal kind of code viewing tool. So if you turn that on, you'll see little annotations in your tooling, and it shows up in other ways as well. But those are the two main ways that you can have this daily snapshot, and you can have the interactive use. I think interactive use is much more popular. It's much more responsive. You'll see people actually kind of fixing their code based on it. But for teams which are really on top of code health, they're going to be using the other means as well. Okay, so in terms of lessons learned, I'm going to go through this quickly. One is naive approaches go farther than expected. So this is part to Matt's point. Yes, start simple and add more interesting things as you go along. Don't try and start hard. One of the things we learned, the opposite, was that our model for the analysis was a relational model based on a logic. Really cool, terrible idea. So ultimately, it's panned out for us. It's valuable. But starting there was a real mistake. It's incredibly complicated. We didn't have anything the literature was actually based on, so we were just making things up as we went along and really learned the hard way. If we had started kind of with the simpler, standard kind of textbook models, I think we would have been much better, and then improved on it. By that point, the project would have been more mature. A lot of other things would have worked out. It would have been a better time to kind of go and try and get more precision and so on. That said, for all, whatever we're doing, the limitations, for example, about the kind of the helper functions, which I said, it's good to hard code some common patterns you'll see. Go ahead and hard code those. So helper functions is the kind of thing we're thinking about. Should we just add support for if it's a one-line function, it's just a return, allow that, because that's so simple, it's probably a helper function and it's probably safe to interpret that on the spot. And the final point is that just the user experience is crucial. Again, this goes back to tens of thousands of developers. Make sure they can understand what they're looking at when they get a diagnostic, understand how to fix it, know where they can look for documentation. Okay, so any more questions? That's the end of nullability. We're going to move on to other topics. Any questions? Yeah, Z.
Does this generalize across smart pointers?
Yes. So everything we've done here, we did for smart pointers. That was another lesson. We were like, oh, how long will it take? 2 weeks. Did not take 2 weeks. I don't even think it took 2 months. But yes, at this point, they're fully supported. The only weirdness is that for smart pointers, you put so for raw pointers, the annotation goes on the right. For smart pointers, it goes on the left, just like const. And our users are like, well, why are we doing this? Like, well, it's the language. Okay, so next topic is spatial safety. And the challenge here we're thinking of is, can we solve spatial safety for C++? And this is modulo other safeties. So again, you could get something that looks like a spatial safety error, which is actually temporal safety or whatnot. But we're actually kind of aiming high. And this is because it really looks like possible to completely eliminate the class of bugs we associate with spatial safety. Okay, what are the challenges in this space? The number one challenge is container indexing itself. So you have a container and you try and get an element, is it bounce checked? Kind of standard bounce checking. But there's also just pointer arithmetic. There's still, it's not a lot, a few percent of code in our experience, but people definitely still write code using pointer arithmetic. Iterators are their own kind of problem. They're kind of a mixture between spatial safety, kind of the bounds elements. They're pointers, say, into your data structure. Maybe they're not a pointer, there's some abstraction, but the bounds checking is a key point. You also have to deal with invalidation. So for this part of the problem, we probably would just focus on the bounds aspects, but in general, they are an interesting challenge in being a mixed bag. C-style strings aren't related to size, but they still have, inherently, the allocation has a size. You want to not run off the end of that size. So they don't pair a size with them. So that's its own kind of challenge. You have to, I think of that as kind of null terminated is its own thing. And then at a meta level, anything you do for your own code is great, particularly if you want to rewrite it or tell your developers to handle it differently. Third-party libraries, though, you have to, generally speaking, are kind of set in stone. So you have to figure out how am I going to do a solution which will work with those. So those are the kind of the challenges as we break them down. We're starting small. We're just focusing on indexing, that is bounds checking, and getting rid of pointer arithmetic. And I'll talk about those now. For that, we have what we call a safe buffers project. The idea of safe buffers was originally proposed by Apple in a Clang RFC back in 2022. We started working on adopting this in early 2024, kind of just encouraging users to move away from pointer arithmetic, use views and containers whenever possible. And it kind of has two aspects. One is to always use a size-bearing, use a container which is bounds checked, which has some size with it. So avoiding C strings, for example. That has two components within it. One is that you need to actually have bounds checked containers. So a primitive array, for example. We know and love those from C++, from C, back in C days, and but those are not bounds checked. So adding that, hardening.
Love,
what?
When you say love,
I don't literally mean. These are a classic artifact from the very earliest days of C.
I just wanted to clarify.
Yes, yeah, exactly. So in fact, I've been impressed looking at the code base. We don't use them that much anymore. Vectors really have replaced, people don't use kind of primitive C arrays, but they still exist. So harden those, okay? And then all your core container types like std vector have to be hardened as well. So that's what kind of bounds check your containers, and then replace, actively go ahead and replace any place you can pointer arithmetic or pointer indexing with some sort of safe abstraction like a view or a container. Okay, so what's so hard about this? This is like that old kids joke about a door. You have to figure out when is a pointer not a pointer, and that's when it's a buffer. And this goes kind of back to the same idea we saw with nullability. C and C++ pointers conflate a lot, right? It's not just the null or not. It's also is it a pointer or not? It's also is it owned or not? And I think you can add more to that list. So our challenge is to look at the whole code base and kind of just pull a pointer out of the hat. Is it a buffer or is it just a singleton or something else? So you might say, why is this so hard? These two cases seem to be covered. If it's an array and it kind of decays to a pointer, well, fine, we can see what it is. Or if you use it as a buffer, fine, you know what it is. All's well and good. And that works for starters, but there's more, right? You have a whole cool graph. What happens when you have a pointer p which is passed through? So it comes in as p, something happens and it's passed on to foo or zab. Now what? You don't see either of those. Worse, you can have a mixed use. So in this zab here, the zab might use it as a singleton, while foo from the kind of the previous slide might be using it as a buffer. So if it's a mixed use, now what do we do? It's neither one nor the other. And perhaps most challenging is external code, right? If zab is somewhere defined elsewhere, so it could be extra and C, that's just an extreme example. It could be you're updating your project, but you can't touch others. Or you're updating your code, but you can't touch third-party code. You need to draw a boundary. Those boundaries are in part kind of the most interesting part of the problem, the hardest part of the challenge, because you have to figure out what do I do when I cross that boundary? And part of what you do is that you lose information. You don't know what happens on the other side. Okay, so we end up with essentially a triple predicate. One is kind of that source. This pointer can hold a buffer, and this is like a reachability, but kind of forward. So there's some allocation or some primitive array which decays, and it can reach this pointer. The other is the opposite. It can be used as a buffer. That is to say, from this pointer, we know it can reach some use. And finally, it's not disqualified along the way. And it's not disqualified by this loss of precision that comes from those examples I gave. And so we're going to have to do something which kind of essentially computes these subsets over the code base and then intersects them. And that gives you this, can and should replace. I mark that second one as an optimization because if it's never used as a buffer, the fact is you still could translate it. You're saying its source is a buffer. It's not used as something else. It's a buffer. Let me just translate it. So that you can kind of decide. You can say if it's never used, there isn't really much point. You can say in the future it might be used. So that's why I mark that. That's in some sense not necessary. Okay, so our solution is basically, it's an inductive solution. It's transitive over the code base. It's computed iteratively. It's inductive because those first two cases I mentioned, kind of the easy cases, those are the base cases. You see either of those and you kind of know, yes, it's being used for those. We've decided to kind of break this into two steps. First one is to summarize any translation we look at. Basically extract all the pointer flow, create a graph of that pointer flow, do that for each translation unit, and then iterate and solve this graph problem over the resultant graphs. We are partway along, so we don't know yet whether the collection of all graphs from the entire code base will fit into, say, one memory, or whether we'll have to solve this in some distributed way. Along the way, once we have these graphs, a useful thing to do is to cluster them. Because this is a large code base, we can't do an atomic commit if we want to kind of update these pointers to a some sort of safe buffer abstraction. So we're going to have to kind of cluster which changes go with which ones have to go, so you won't have a break the code by committing. So once we have these graphs, we can do the clustering, and then finally, you've done the analysis, you've done the clustering. Now we can actually apply the edits. For example, you could move a raw pointer change it to be a span. You can change the uses might have to change. If it's indexing, well, as an overloaded operator, you probably don't have to touch it. But if it's kind of translating, it's assigning to a pointer, which then uses it as a singleton, well, then you might have to do some sort of coercion. For anyone familiar with F-bound safety, the Apple's working on for C, they have their own set of different annotations for pointers. So you can imagine at this point you stop, and instead of editing towards safe buffers for C++, you actually produce annotations from the F-bound safety pointer annotation set. We're just starting with the actual rollouts, actually the development and whatnot, so we don't know exactly this work out, but by kind of manual evaluation of the safe buffer warnings on our code base and by looking at the WIP ASAN findings, that's kind of a Google-wide run of ASAN, which does sampling. Looking at those, it looks like the various approaches here will cover about 70–80% of the safe buffer warnings and about 50+% of the bugs we've seen and fixed for out of bounds errors should be prevented by these approaches. Now, some complications. Ownership is one. As I said, pointers also conflate ownership, and that determines which safe buffer abstraction. I'm kind of waving my hands there. Like spans are good if it's not owned, but you might want to use like a vector or something else if it is owned. And so we have to figure that out. So we need some sort of ownership detection. Unique pointers are their own challenge in that they are relatively recently introduced. They tell you that it's a pointer to a buffer, this particular version of unique pointers, but there's no size. So now we have to go through and replace all those unique pointers to buffers with sizes. We actually even introduce a kind of a unique array, we call it, which is just a thin wrapper. But that's still, you have to pick those up and figure out where the size is and how to pair that together. So the basic status here is that already last year, Google enabled bounds checking across our fleet for the C++ standard library. The impact was lower than we expected, only about 0.3%, so significant, particularly at our scale. But we are rather pleased by what we get for what we pay was well worth it. We've completed automated migrations for some examples of kind of new allocations using kind of RAI setup. So these are cases where someone allocates on the heap, but it really, it's probably just because the size is essentially still stack local. So we can replace that with something, not vector, but something like vector. Vector has the wrong semantics. We're nearly done with the unique pointer migration. We're piloting deployment of primitive array hardening. So we're basically at Google, we're going to have a new semantics for primitive arrays. They're going to be bounds checked. And finally, we've just gotten started on the implementation for the tooling I was kind of sketching. It's going to focus on adding translating to spans, and that's gotten started. That does leave some hard problems, iterators, C-strings, and third party, but we do have some ideas inspired by F-bound safety for how we can kind of get, solve those as well. Okay, so before I continue with the next, any questions on that?
Could you just talk about the primitive array bounds checking?
Yes.
So how? You mean just like a C-style array?
C-style array. So the Cling has a flagged F-sanitize array bounds. So we're basically doing some tweaking, basically a few improvements to that. But basically that was almost ready-made, and it will either reason statically about the size or insert a bounds check.
So does it stash this? How does it know how big the array is?
Well, primitive arrays has to come with a size.
Yeah.
Yes, they're not allocated.
So there are multiple competing implementations for this. Apple is also working on that, right?
Yes, so they
array bounds, they upstream that for Clang.
Yeah, I think they're contributing to that one. I mean, no.
No.
So bound safety, bound safety does have its own, and that is separate from sanitize array bounds. But yeah, so we do have to kind of get onto the same page. That's definitely one of the upcoming challenges. We've been talking to each other quite a lot, so it's a good rapport, but there definitely are things to look at. Yeah.
Why not push towards something like a ref to a std array instead of like this approach?
So we definitely consider, instead of primitive array.
Yeah.
Yes, this was, we actually thought, when we started this project last year, we thought we were doing exactly that. And the pushback against std array is that it's rather uncommon, that people don't use it very much, and that it adds significant compilation overhead. So just the fact that it's a template, and that you're now going from places that didn't need to use that template, you're adding that header, and the template instantiation is costly. I did not look into the claims about the point about overhead. This is from Chandler, so I just kind of took it on good faith. But the argument that developers, we basically did actually a full chart of the advantages and disadvantages of each. It kind of came out even, and then it came down to this. It kind of pushes over the edge towards one because of the compilation overhead. But there were like 11 different factors we came to in terms of developer experience and whatnot. So it's messy. Like, it is not an obvious. I don't think it's obvious either.
So would you go so far as to push a user away from that then?
Using std array?
Yeah.
Once you do hardening, then yes. But it really depends on the context. If you're not in a context, or you need to be portable, you can't rely on it being hardened, then I think std array is reasonable. Yeah.
I think I'm a little confused here, because it seems like array versus std array is totally orthogonal to the question of you can harden either of them, right?
Yeah, where std array already is hardened with the standard library. The question is, do you additionally harden primitive arrays, or push people towards the hardened std array? Yeah.
Is there a relationship between the iterative bound safety solver you were describing and the Spanifier tool in the Chromium project?
Yes. Yeah, there is. In fact, I should have mentioned that. So we're talking to each other. It is unfortunately we can't share code just because they're targeting open source and we're not. But like the actual ideas, we talk regularly, and the ideas actually go in both directions. Started they were just giving us ideas. They had an awesome design document which definitely inspired our work. And then this whole idea of bounds crossing is something they're only learning now from us, kind of importance and how to solve that. So yeah, I'm hoping someday we can just unify the tools, but for now they have a much smaller problem, and so they're not solving as general problem because the code base is so much smaller. So it wasn't worth unifying the source. But yeah, it's basically an identical problem. Okay, so next up is initialization safety. So why is this a big deal, right? I think this is the easiest one to kind of brush aside. So here's a kind of somewhat contrived example, in that you have some function maybe launch. You declare the bool launch, it's not initialized, okay? You have some logic which you really think is going to initialize it, it doesn't. And then finally, whether or not you launch that rocket now depends on what was on the stack beforehand. What was on the stack beforehand actually might be something that an attacker could control. That is it's a common way of using the stack against
current compilers give warnings about this.
So something as simple as a bool, maybe not. But there are more. Yes, this is a somewhat contrived example. There are definitely more examples of you can definitely get uninitialized memory, which you will use, and you will not be caught by the compiler.
A very easy way to hit this is like if you define a std array without curly bracket. This hit me personally, and then you write into that memory, but it's not initialized.
Yeah. So I think you can put together, you can say either it's initialized or the compiler catches it and warns, but either way, you want to make sure that you can't access uninitialized memory. Okay, and there's multiple parallels from this. One is just, leaks. You could leak user data, you can leak a pointer, which if an attacker knows the format of the pointers, that could break ASLR, which is a particular memory layout protection mechanism. You can lead to data corruption. Again, if it's a pointer, you might end up writing to parts of memory you didn't mean write to. Or this one, I found this a little amusing, but it's not amusing necessarily, that if some delay in your program depends on uninitialized memory, you can end up with arbitrary delays, which when you're debugging, arbitrary time problems that are flaky are really annoying. So all these kinds of things are bad for the user experience and is generally bad for security. So the obvious solution here is just initialize all the things. Why are we making such a big deal about this? And I think there's a proposal in 2026 to do just this or something related. But right now, the challenge is twofold. One is the major thing is initialization isn't free. And when you're looking at us for fleet scale, that matters. We have to take that into account. We have to be really careful any added kind of performance hit, particularly if it's on average low, but like it hits one team or one project particularly high. Another interesting thing is that zero init actually isn't always a good fit. I would say 20 to 40% of cases, zero init is the wrong init, which means they should be doing something else. They're missing the init, but it's not zero init. If the language defines zero init to begin with, I think it's a different situation when you're kind of backporting it onto the language where you now might make things worse, possibly just by suddenly adding zero init. Okay, so the basic approach is to add stack variable initialization in the compiler, and then you can rely on dead store elimination that in the optimizer to get rid of any stores you've added that aren't necessary. We're adding this to the compiler versus rewriting the code, and you notice this is different from the previous two projects. This is a trade-off. You cover more code, out of bat. You just turned it on the compiler. Anything which is being compiled is covered. You don't have to change things. That's great for third party. On the other hand, you have to be more conservative because the compiler really, there's no code review. They generally kind of what the optimizer is doing is a much more conservative assumptions what we can do in our code rewriting. We're playing it more fast and loose. We've got reasons why we can do that, not least because of code review. And there are other differences as well. Those are kind of a key trade-off. We're focusing on the stack in part for performance, that if you make a mistake, kind of the cost of redundant stack store is lower. But also for security. In practice, the stack is much more heavily used for exploits than the heap. Okay, so as I said, we rely on dead store elimination. That's not enough. We actually had to improve dead store elimination. Kind of just quickly, we did two things. One, we added annotations to allow for interprocedural information to flow in dead store elimination. So that's even within a translation unit, different things are happening in different functions. Allow information like the callee initialize this so the caller doesn't have to, or vice versa. And that will allow kind of the optimizer locally to make, within the TU to make changes. But then we also needed to do better. We need to export this to surface this in ThinLTL. ThinLTL is Clang's link time optimization framework, so that you could get kind of whole program optimization of the same kind of quality as within a TU. The nice thing about this, what I really love, is that when you make these kinds of changes, you kind of just do the simple thing in your whatever change you do, but then improve the optimizer, then the benefits accrue to everything, right? It's not just your change that wins. This is available now in Clang with the ftrivial autovar init flag. It actually supports both zero and pattern init. Pattern init addresses this issue of zero init. Pattern init isn't going to be the right answer, but when it goes wrong, you can tell that the code, it's weird, right? You print out the hex, you'll really notice it. So that kind of gives it advantages for debugging. We actually have enable this for all of our unoptimized test builds. The DSE improvements are upstreamed in Clang. And based on early estimates, this can be added and be turned on for a less than 1% overhead in the optimized builds. So we have not yet turned this on in production, but it is available, and I think you could try it out for your own system. I'm going to take a drink because I am dying there.
So I think something like that is coming in C++ 26, right?
Yes. So I forget the exact relationship, but yes, I think it's more, in fact, than just stacking it. So we did more. We have a whole heap in it thing. I just didn't want to get into that because I didn't land. Yes.
So one of the cases of like uninitialized variables is when you have an output parameter and then you forget to initialize it or something like that. Have you looked at like annotating output parameters, being like, this is an output parameter, and so the compiler then like having the compiler check to make sure that it was initialized in that function?
I think that's what the interprocedural kind of support in the Desert elimination, I think, covers that. It will see the output parameter as initialized, will mark that on the boundary so that the caller can know that.
Oh, so it's part of the optimizer. It's not like an annotation, like an attribute or something that we would put.
It's an LVM IR attribute.
I see. So
but not a user attribute.
Okay, so my question is, have you considered like user level attributes? Because there are extensions in a lot of like a lot of compilers where it's like _out or something where it says it's an output parameter.
Maybe. I don't remember the exact details. I took over this team when that was in progress. So that particular detail, I don't remember if we considered or not. Yeah. Okay, so let's just talk briefly about our foray into temporal safety. Temporal safety you can think of as kind of a combination of lifetimes. You have a notion of a certain memory in general. You can kind of think of it, it's valid here. This is where it starts being valid, and here's what kind of ends being valid. I mean, it's called the lifetime of the memory, and you often have relationships between pieces of memory as to kind of, yes, if you take a pointer from that, as long as your lifetime is shorter, that's okay. If it's longer, it's not okay, because now you could actually have a pointer to a piece of memory that has already gone out of scope. So that's lifetimes. But there's also some kind of validity where you might have a pointer into a data structure. The data structure, like a vector, say, is allocated at the beginning of the stack and goes out at the end of the stack. So it looks like it's valid through the whole scope. And yet, if you modify the vector, suddenly the pointer into the vector clearly is no longer valid. And so validity is kind of a separate thing. And this is, if you're familiar with Rust, this is not new. This is the whole reason there's borrow checking and exclusivity. It's about kind of handling these two aspects of temporal safety. In general, we found that temporal safety is harder to exploit. So this is why this project, I will spend 2 slides on this, is kind of working on later. We're focusing more heavily right now on spatial safety, but we don't want to kind of leave this behind. But it's also harder to solve, and that's the real truth. I think that the reason, it's low-hanging fruit is always a good place to start. And that it seems like any static solution is going to require major changes to the language. Look at the difference between Rust and C++, and think about the challenge, as I think Andy and Matt have thought about, going even from C to Rust, all the more so C++ to Rust. That said, again, with this philosophy of, well, can we eliminate kind of, subsets? Can we identify bug classes that we can eliminate? There are 2 pragmatic kind of subsets we can focus on, which we're looking at now. And Mehrdad has been a major player in some of this work, particularly the lifetime attributes. There's lifetime bound and lifetime capture by, which are both supported in Clang. And they are kind of particular forms of kind of lifetime relationships, which you can express with these very simple annotations. They're implemented in Clang. They work at the statement level, so they're kind of limited. And the idea is that we're working now on an RFC to extend these, their basically their enforcement and their meaning to the entire function scope. So basically keep simple, but then make them more powerful in terms of the actual what they can accomplish. At the same time, that's not enough. We would also like to focus on the challenge of interoperation with Rust or other languages which have you want to use Rust-style lifetime annotations. And so we're working on, basically there's a 2022 RFC for Rust-style lifetime annotations with C++. We want to kind of revive that and get that rolling this year, work with other players in the industry who are interested in trying to put together something which could be accepted, at least kind of in Clang, and we can think, beyond that, the standard or whatnot. Okay, so kind of just to close. These are a lot of projects, a lot of years on these, kind of trying to compress this down to a few ideas. So this is somewhat random, but the first one I would say is that when working on these kinds of analyses, I would say solve for the code base. So I've kind of gone through an evolution, myself, in that I saw some early work. Hiram Wright actually published a paper on this where it would do almost like a peephole optimization, a peephole rewriting. So basically identify a very local pattern. You're kind of moving, say, from one type to another. Change that and now leave the code so it can compile, and then that will trigger other patterns, but do each one as its own pass. So you kind of just keep on rewriting the code. There's this constant churn. You can then up that to use. So I wrote a tool which was something else, but kind of the same idea, moved to looking at the entire translation unit at a time, and that's great. One translation unit at a time, but then if you want to spread across translation units, you again kind of keep iterating over the code. We learned that this isn't actually, I think, the right approach. I think the right approach is to step back, model your problem, and solve the problem for the code base. Now, notice that's not incremental. The idea is you're looking at the whole code base and solving. So you still want to stick to incremental in terms of rolling it out. But for solving the problem, you can actually look at the whole code base. It gives you a lot of information, write your analysis that way. And then the results of that analysis can then be turned into incremental patches. So that said, incremental solutions are essentially your language design. Anything you're doing statically has to be something that you can roll out incrementally. Otherwise, you'll just, unless you, again, have a small code base, which you can do with one atomic change, you'll never get where you're going. On top of that, we found that kind of having a very low false positive rate in the enforcement tooling, the diagnostics, is really important. Again, particularly the more developers you have, the more culture, subcultures you'll have. If you have some team with one project, you can have someone says, this is the way we're doing it. It's annoying, but deal. That's not good, I think, in its own right, but that works. It doesn't work once you scale up. You just have too many different cultures, and you will not get that authority. And if you try to exercise that authority, you'll just you'll undermine yourself. So you need to kind of make something that works with the user where they are. And the final point here is building relationships. So coming back to kind of the human part that I think is very easy to focus on the technical, and for us, for sure, that this is happening, realizing that working with, project leads, people who are actually in the trenches and have experience with null pointer crashes and the like, they can give you perspectives that you just wouldn't have seen. They'll actually see problems you wouldn't have seen. And they can also just validate you. This is something you're working from some central location. You have an idea, you think this is the right thing, but you can kind of be blinded by this sense of I don't know, maybe. If you're speaking to someone who actually has experience who can validate that also is powerful. They also can work with their own teammates and can convince them to kind of onboard them. So there's just so much value, kind of technical value you will get out of building those relationships, and working through them and making sure you get there. Even if it means you'll get there slower, you'll get to the right place versus the wrong one. Okay, so finally, I'm just going to prognosticate a little bit about C versus C++. These are my opinions, not those of my employer. The whole talk are my opinions, not those of my employer. Okay, so the first thing is I want to admit upfront that safety definitely requires effort. Okay, it requires effort in terms of system development. All the work that we're doing and we're talking about, this has been many years worth of effort. And there are many other people in the industry and in academia who are working on this. So yes, that's there. That has to be done. But I think, again, working together, we have made tremendous progress. It also takes effort to apply it to your code base. But there's also really good automated solutions. They're getting better all the time. With LLMs, I think that's going to take another leap. But the two working together, I do see a future in kind of the kind of automation we focus on and that kind of automation. And I think it means that we will drastically reduce the cost of getting to safety. And safety also pays other dividends. It's not just now your code can't be exploited. it improves your code. Your code health improves. Your developers will like that. You'll like that. And it leads to better interop with these new languages, which I think even if you want to stick with C++, it'll become unavoidable, if it's not already, to interoperate with Rust and Swift and the like. The theme I kind of keep harping on here, that if you're going to be working in this area, I think limiting bug classes is the way to go. Like sometimes you don't have a choice. You need to kind of, you have a problem now, you need to mitigate it, fine. If you're looking to kind of invest and think for the long term, think about how to identify an entire class and wipe that away. And finally, no matter what, this isn't a binary choice. That's why we're not looking to say we're going to get to a perfect future. Perfect is the enemy of the good. We really think we can make incremental changes, keep moving C++ forward, even as we start increasingly adopting other memory-safe languages, we can keep making C++ better. Before I finish, I want to acknowledge this is, I've been involved in any of the work I talked about, but this is not my work. Many of the people here, everyone here on the slide has contributed in one way or another. Actually, Mardad as well. I'm sorry, forgot about you. And others. A bunch of people in the Clang project, Teas, we have other reviewers, and so this is really the work of many people. And I can't possibly name them all. Okay, and that's all. Questions about any of those projects or anything related?
Are you going to publish another? There's a great blog post published about the 0.3% regression from that. I would really love to get a similar blog post about the initialization of stack bars.
We don't have plans now for that. That is kind of the bottom of the list of stuff. So that's like backburnered. Like we got to a point where we can resume it. We are not pushing that forward like it's available, but no, not yet. So that could be. I don't know if I get headcount. Always asking for it. Yes, but not in the foreseeable future.
As in the publishing it or the implementing it? It's not.
Turning it on and therefore kind of publishing. I think publishing could follow easily if we turned it on, but actually doing the work to measure it was challenging. That was one of kind of the blockers of how do you kind of meaningfully, since it's so small, meaningfully kind of getting those measurements. You can't do the same thing that we did for hardening. So yeah, that's one of my regrets is that we did not get to roll that out. So again, we rolled out the pattern in debug, and it's available. But so it's opt-in available. We don't have plans to enable it fleet-wide just because of the difficulties of figuring out the cost and keeping it low enough.
So what makes it harder? So for hardening, you could count the cost. And
yes.
So why not here? Like, what's the difference?
In hardening, you can look at the time spent in the hardened asserts, essentially. You can look at, are you executing that instruction writ large?
Okay, you're not actually measuring the whole thing before and after?
You are, but the whole thing is a dynamic system that changes because they're developers developing all the time.
Right.
Yeah, we don't have A/B testing. The kind of the A/B testing you'd want for this in production has been coming for a few years now. And it's kind of arrived, but So there's basically a framework we would need for testing in production to do the A/B testing, which would really answer the question, which is just not available yet. And so what we've done are kind of low tests, which just don't give you the resolution we need. And then to go beyond that, you have to speak to individual teams, and everyone's got their own setup. It basically kind of got into the weeds of complexity.
So let's put that 0.3% number. That's actually what, sampling or putting RDTSCs before and after, or
that's some form of sampling,
but it's sampling at the scale of Google's fleet.
Yeah.
So law of large numbers really, really applies.
Well,
I'm intrigued, but
if your methodology is not, in this case probably I won't say flawed, but not perfect, then the laws of large number just give you a wrong number with higher confidence.
Yes. If your sampling is biased, the result of your sample is also biased.
I'm just wondering whether the sampling would actually overestimate the cost, because CPUs could be quite good at sort of parallelizing things, and that
So I don't know if
check might cost less than even less than that.
I don't know if this answers your question, but the thing is, like, when you make that change, if by the time you roll out that change to the whole fleet, a lot of people have made a lot of changes to the code base.
Yeah.
So if you see a 0.3%, is that due to your change or due to the thousands of other changes?
Yeah.
And that's I don't know of any solution to that really. It's just
A/B testing. A/B testing.
Yeah, you have to have a good load that you can test it on. And
I don't think Google has a problem generating load or finding load. I think would be a more.
But you can say 0.3% of the instructions executed fleet-wide are the instructions the compiler inserted for the offset.
So that's probably an upper bound.
Because when it gets inlined, the attribution is sometimes wrong with like, the DPF profiling. So it doesn't. It's not totally
Can we just clarify what the number being reported is? Is it sampling that says was the CPU on this instruction, or is it counters that say like how many times did I execute the instruction?
It's sampling that says was the CPU on this instruction.
Okay, thank you.
Yeah, this is an area I don't. This is one I was less involved in, so I don't know exact measurement methodology. But Matt, ironically, who's no longer at Google, has been much more closely involved with that kind of architecture, infrastructure. Anything else?
Oh, one thing, just going back a little bit, surprised me a little bit about the initializer thing. You said you enable it for debug builds, but is that like debug with optimization builds?
No, without optimization.
Does that,
It's not a fast build.
That is a bit surprising because I thought, I never tried this, but I thought that for an optimized build, like some place where like variable is not initialized, the LVM would already put poison in there or something like that. I'm a bit surprised that's not the case.
Yeah, it could be in some cases, but not all.
Oh, yeah.
And the reason we haven't done optimized builds is, again, this is a silly technical issue. It's easy to tell the difference between a debug build and an optimized build, right? But an optimized build for test and an optimized build for production, there is no particular indicator, so we would have to add one to know that we're not adding this to production. But I don't think there's any reason it shouldn't work well with the optimizer, but we just can't right now.
To test an optimized mode, run thin LTO. You may be able to use thin LTO as your proxy for prod.
Yeah, I don't know. It's a good question. Okay. Well, thank you.
Thank you.
Thank you.